Okay, all right, everybody. Let's get started. It's 2 minutes after 1. So this is the beginning of the CDM Research Colloquium series for this academic year. We are trying to try something different. So the plan is to have this colloquium here in this room, which is a trimodal room, and we are going to have speakers who are going to come in person. But then most of the speakers are going to be remote. But still, we will plan to have it here. No matter the speaker is in person or remote, we can do it from here. So that's the plan. We'll see how things work out. So with that, for the first talk for this series, I'm delighted to have Dr. Sanjay Krishnan. He's an assistant professor in the computer science department at University of Chicago. His research group currently studies corrupted, missing, or otherwise uncertain data in database and information retrieval systems. They are currently studying systems that can give certifiable accuracy guarantees in partial complete databases, query accuracy evolution in corrupted databases, and also automatic detection of data leakage. For today, his title is going to be Histograms and how to make them better. So I'll turn it over to Sanjay.
Great, thank you guys all for having me. This is my first talk in person in like 2 years.
Okay, so when she stopped, yeah, I'll let you know for sure. Okay, thank you.
Perfect. Okay, good. So this is the first talk that I've done in person, I guess in person-ish in the last 2 years. So I'm a little bit rusty. So I've made this talk a little bit high level. And if you guys are interested in any details, please feel free to stop me and we can deep dive into something. So a little bit about this project and what I'm going to be talking about. So my academic background is in studying compression, studying information theory, and studying how small we can make data and still get meaningful insights out of it, right? And this entire research project started about 2.5 years ago, where I got a question in my graduate seminar about histograms. They said that, like, we learn about histograms in AP statistics in high school, right? And they're used everywhere in computer science, from visualization to database research to all sorts of data summarization applications to computer vision. They're used everywhere, right? Why don't they work in high dimensions? And this was like the starting point of a 3-year research agenda where my group really deep dove into high dimensional data summarization. And it all comes back to the basic thing that we all understand as a histogram. So before we even get into any of that research or get into any of those details, why are we studying this in the first place? So I basically believe that there's a basic tension between the data growth in our society and the processing capacity that we have. Data is fundamentally right now growing faster than the amount of capacity we have to process it, right? And there are many reasons for it. There are energy reasons for this. There are fundamental physics reasons for this. But at its heart, right now, data is growing faster than compute. And depending on who you ask, whether you ask an optimist or a pessimist, we're roughly at that inflection point, right? That, like, maybe a little bit to the right, maybe a little bit to the left, who you're talking to. But fundamentally, data is growing faster than compute. And what does this really mean for the real world? You guys as computer scientists in the audience, what does it mean for us that data is growing faster than compute? That means that as our data sets grow, stuff is going to slow down. We're just not able to marshal as many resources as we can to keep up with that growth in data, right? This means that tomorrow, if you log into your website, it's going to slow down as more users come in. It means that tomorrow, if you're trying to train the next best deep learning model on more data, it's going to take longer to do. We're just fundamentally, our processing capacity is not growing as fast as the data that we're collecting. So this was the start. This is the real motivation for research into a branch of computer science called data synopses. So we have large data sets. Can we take these large data sets and construct a smaller dimensional synopsis data structure? So that means that we take this big data, like for example, something that looks like a table over here, come up with some sort of an algorithm that reduces the size, summarizes it, captures the essential trends and components and the essential sort of data that is in there, and allow us to process that smaller size synopsis. So imagine that I have a big company, I have all the master data from all of my customers. Is there some efficient algorithm that we can come up with that summarizes that guide down into a nice, small, little fixed size representation, and I can do some approximate processing? Now, of course, this is only going to work in places where approximation is tolerated. But there are so many applications in our world where approximation is, right? For example, visualizations. We only have enough resolution on our screens at pixels, to individual pixels, right? Like getting something to the point, to the like sixth decimal point doesn't really matter when it's being put onto a 1024 by 768 screen, right? Similarly, in a lot of other areas, approximation can be tolerated. So this is kind of the core piece of my research. How do I take large data sets, extremely large data sets, summarize them in terms of synopses, and do approximate analytics? So what does this look like on the graph that I showed you? The idea is that if you can summarize a large data set with a smaller representation, you can sort of match the impedance of the rate of processing growth, right? You can sort of take that big data, reduce it down, albeit for a loss in accuracy. You're going to potentially not be able to do everything you can do with the big data, but you might be able to do a lot of important applications keeping up with the growth of processing. So that's kind of the high-level motivation. And now I'm going to sort of talk about the actual technical details. This whole project really started about a study of histograms, why they work, when they work, and more than you ever wanted to know about them, right? Then I'm going to talk about how we took these basic insights about one-dimensional histograms and translated them into higher dimensions. How do we sort of build a general-purpose data summarization system that is based on like some of the mathematical intuition we got from histograms? And finally, I'm going to say like how all of that work might have been useless and we can just throw machine learning at this problem and get some really cool results. So that's kind of the outline of the talk. But before we start, are there any questions from the audience about the motivation, why we're even doing this, or anything along those lines? Perfect. If there are no questions, we can sort of go into a sort of simple example, and this is the example that I like to use when talking about histograms in my class. So just to get everyone on the same page, what is a histogram? So let's think about a data reduction problem in one dimension, okay? So imagine that we were running a survey, we were on the blue line, and we we're collecting ages of the people that we met on the blue line. We just went passenger by passenger and asked them what their age was, right? So to characterize this data set, it's a one-dimensional data set. We're literally getting one measurement from each participant, okay? This entire data set can be thought of as an empirical distribution of ages. We have ages on the x-axis, and we have frequencies on the y-axis. There are potentially more people over here, there are less people over there. That's what this distribution captures. So if we think about how much data, how much information content is in this distribution over here, we sort of have 70-ish unique values and 5 bits of resolution, right? It goes roughly up to 32 over here, right? So it takes 350 bits of resolution to fully characterize this data set that we captured, right? So what is a histogram? A histogram is a way of discretizing the domain of ages. It is a way of discretizing this distribution in a way to reduce the amount of storage that we're using to do this, right? So for example, we can start off with the empirical distribution on the right and go to the histogram on the left. Fundamentally, histograms are exploiting smoothness in real data distributions, right? This is something that we often don't think about. We often think about a histogram as a compression tool or a summarization tool. But what is the inductive bias that it's using to actually compress it? It is exploiting smoothness. It's basically exploiting the fact that nearby values are going to have similar frequencies, right? It is fundamentally exploiting smoothness in the distribution. This is what it's doing, right? So that means that if I go onto the blue line and I ask people for their ages, and there are 17 people with the age 46, what a histogram is, the inductive bias baked into a histogram is saying that there are probably close to 17 people with the age 47 or 48. It's exploiting smoothness in this X domain. So based on that idea, what you're doing is you're binning up the domain into buckets and aggregating within those buckets. And this really only works if there is smoothness in the domain that you're binning up. And we can also use this to sort of understand when they break down too. What is the error in a histogram? The error in a histogram is going to be fundamentally dependent on the variation within a single bucket. So the crazier you have a distribution, the higher the variation within a single bucket, the more erroneous a histogram is going to be at representing this data. So let's take our example and see what this particular histogram did. This histogram took these 70 some odd unique ages, turned them into 8 different buckets. And now there are about 7 bits of resolution per bucket, like it goes roughly up to 256 among friends at least. So 56 versus 350. This is how a histogram compresses a data. It exploits the fact that there's some latent smoothness in this probability distribution. So that intuition is going to be really helpful to understand when this doesn't work. And the whole reason that I'm giving this talk is because it turns out it doesn't work all the time, right? So when does a histogram not work? It fundamentally works when those frequencies are not smooth with respect to the domain. Does this happen in real data? I can give you a natural data set where this problem is going to happen, right? Imagine that instead of asking people's ages on the blue line, I went to a CTA bus stop and I wanted to go minute by minute and figure out how many people are waiting in line for the bus. I'm going to get a distribution that looks something like this. There's going to be a spike right around the time the bus arrives, right? Because people presumably check their phone, check bus timings, show up right before the bus arrives, get on the bus, and then there's immediately nothing. These are the types of distributions that histograms are just horrible at. Because if you really think about it, how are you going to bin up the space and control for this variation, right? Within a single bucket, you're going to have a lot of zeros, big spikes, and a little bit of extra stuff over there, right? So these are exactly the distributions that histograms are not good at approximating. So when you get a distribution like this, you have to be smarter about the way that you bin things up. You have to be able to adjust where these bins fall. You can't just split up ages like every 10 years. You have to be more careful about how you cut this distribution to avoid mixing these big spikes with this blank area. So there is an entire body of literature on how to optimize histogram bucketing. And I encourage you to read some of this reference over here. But it turns out that really histograms fail under this problem that we call sparsity. When there are a lot of zeros in your distribution, like a distribution like this, number of people waiting in line in the bus. At any given minute, if you look at a bus stop, there's probably no one there. When people are going to be at the bus, right when the bus is about to arrive, right? When there is sparsity, this is when you need to do more work with a histogram, okay? And so we actually ran a very big study at Chicago where we simulated a bunch of different distributions. We just generated random statistical distributions using a technique called Dirichlet sampling. It's a fancy word for distributions over distributions. And we generated a bunch of different distributions and tried to understand, is this intuition actually right? We have over here the optimal histogram error, so that means using optimized partitioning of these buckets. And we have on the x-axis like an equi-width histogram error, okay? Color-coded, we have the uniformity of the distribution, so how smooth it is. Uniformity is another word for entropy. If you're interested in how we exactly calculated it, ask me offline. So as we sort of see, when things are smooth, there's no real benefit to optimizing everything. You might as well just evenly partition your domain. As things get less and less smooth, there is a regime in which these optimized histograms actually earn their pay, okay? So the moral of the story is, when I have sparse distributions, when I have low entropy distributions, distributions that are hitting on only certain values, I have to be very careful about how I partition my domain to be able to approximate that distribution. So why does this matter? This was kind of our first insight about 2.5 years ago when we were studying this problem. This really matters because a working definition for high dimensional data, a working definition for multidimensional data is it's almost always sparse. why is this the case? Why is high-dimensional data almost always sparse? If we think about all the different attributes, for example, this is some census data over here. If we think about all the different attributes that we have, each one of those attributes has a domain of potential values. However, you have a finite data set in front of you. You don't have exponentially many data, right? You have a finite data set of n, and you're not getting all permutations and combinations of all possible domain values. So high-dimensional data is almost always sparse. So you're almost always in this regime where you have these big holes and big spiky things, right? In one dimensions, you have to come up with this bus station example to come up with a sparse distribution. In high dimensions, the name of the game is sparsity. So why don't histograms work in high dimensions? It's fundamentally because you have an issue of sparsity. If you were to equally partition a high dimensional space, you would have exponentially many buckets. Most of them are completely empty. Okay? So this is the intuition that we started hitting, right? That why don't histograms work? You fundamentally have to figure out some way of dealing with sparsity. And when you really think about it, what is the solution here? Well, the same way in one dimension, we had to be very careful about figuring out how to partition the space to eliminate that sparsity. We're going to do the same trick over two projects. We're going to figure out how to partition the space to sort of to cover out that white space, figure out how we can skip that white space, right? We're also going to figure out ways that we can project things onto lower dimensions so we can be able to exploit that to sort of densify the data. So that's going to lead us to the first project that we have on adaptive high-dimensional histograms. And I put histograms in quotes because they're not really histograms, but they're going to be things that like look and behave like them. Good. Are there any questions? Perfect. So let's think about a histogram at its sort of essence. What are we actually doing here? So I put like a little forget about numbers, forget about ages on the seat on the blue line, forget about bus stations and so on. Let's just think about this in the abstract. What are the core computational operations that we're doing? So let's imagine that we have a domain over here that is just represented as a line. What a histogram is going to do is it's going to partition a domain into disjoint partitions. That's kind of step one. We're constructing a set of disjoint partitions that span the domain. Step two is we're going to take those disjoint partitions and calculate some sort of an aggregate statistic that represents the data in that partition. Okay? For example, like in the histograms that I showed you, we're just calculating the count. We're calculating the frequency in each one of those partitions. Okay? So step one, we take a domain, break it into disjoint partitions. Step two, we summarize the data within the partitions with an aggregate statistic. So there's actually nothing in this definition, in this sort of core definition of a generalized histogram, there's nothing about dimensionality or frequencies or anything. There's nothing about representing an empirical distribution. There's nothing about sparsity. It's just fundamentally a computational operation where I'm taking a domain that I care about, breaking it into disjoint partitions, and summarizing each one of those disjoint partitions with some statistic that I believe is going to capture the essence of what is in that partition, right? If I'm representing a distribution, the natural thing to do is a count. I could also take something like completely different. For example, I could build a two-dimensional kind of a histogram, just like, for example, over ages and heights. I could take all of the students in a classroom, break up ages into a set of disjoint buckets, and calculate the average height per disjoint bucket. That's kind of fundamentally the same thing, right? It's like essentially the same computational operations. It's going to sort of behave the same. The same principles hold. You're exploiting smoothness in the domain. You're exploiting the fact that people who are close at age are probably also close at height, right? Over here, you're exploiting people who are close in the domain, are close in their frequency, right? You can just take this and sort of generalize this, right? And you can even do this over more abstract things as well, right? These don't have to be point statistics. You could say, for example, I could take the set of countries, split them up into disjoint partitions, and calculate the top K incomes in there. Again, it has the same rough computational things. Now, this might not be meaningful at all, but you could do it, okay? But the same intuition holds. You're fundamentally breaking up a domain into disjoint partitions and summarizing those disjoint partitions with some sort of a statistic, okay? And when is it going to work? When that summary is meaningful, one, and two, when the partitions are meaningful as well. The partitions imply something about the summary. So, when we really think about high dimensional histograms, I want you to sort of think about two different sort of axes that matter over here. You have a partitioning dimension, and you have an aggregation dimension. So when we think about capturing these high dimensional distributions, summarizing these high dimensional distributions, the first thing that we need to define is what we're going to partition on and what we're going to aggregate on. Okay? So when I have a big data set, I need to sort of know up front what I care about partitioning and what I care about aggregating. Right? What are the core statistics that I'm going to use? So essentially the theme goes, when I look at these generalized histograms, I want to partition the data set in such a way that you're roughly homogeneous in these aggregation dimensions. So this sort of, like, when you can sort of take this generalized histogram idea and sort of push it forward further and further and further, right? Like, when I start thinking about just general partitions, when I stop thinking about this in one dimension, I just think about abstract partitions of spaces. Partitions have a lot of nice properties, especially the disjoint partitions that we're talking about. The fact that they naturally form a hierarchy. For example, I can have partitions like this, P0 through P6. Then I can group together partitions at the next level. I can get P1, P01, P23, P45, P6, and I can keep on going all the way to the top. Partitioning, disjoint partitioning of a space follows a nice hierarchy of partitions, subpartitions, and so on, right? This is going to be one of these key algorithmic insights that it's not really clear how we're using it right now, but just sort of trust it, that when you have disjoint partitions, and you have a structure like this, where each layer spans the entire domain, and each parent is spanned by their sibling, their children, then you have a sort of a nice hierarchy, a tree of these partitions. So how could we turn this into an algorithm that we could use? Suppose I have a high dimensional data set and I need to partition an abstract domain. Maybe what I really need to do is to go top down and recursively fix broken partitions. I need to find a way to recursively subdivide a space to build more and more homogeneous partitions for these different aggregation attributes. So suppose I have a high dimensional data set. This sort of gives us a little bit of a recipe, sort of a high level algorithm of how I would approach this problem, right? We found that what we really want to do is to construct these partitions that are homogeneous with respect to what we're aggregating, right? Like whether it's frequencies, whether it's average heights, I need to take the space, start off with all my data, and repeatedly cut in a way to make it more and more homogeneous. Fix those partitions that are broken, right? For example, if this guy has too high variance, maybe I need to subdivide it. This guy has too high variance, maybe I need to subdivide it. This gives us an intuition on the type of algorithm that we want to build here. So now let's go into the actual algorithm that we actually built, right? So that's kind of the intuition, high-level intuition. How did we actually build this and how did we prove something about it? It turns out that this basic intuition is captured in a geometric data structure called a KD tree or K-dimensional tree. This is a geometric data structure that is widely studied in theoretical computer science and computational geometry. It has been used in many different areas, most notably for information retrieval. So that means that I have a point in a high dimensional space and I want to find all the points close to it. You use something like a KD tree. Okay? The basic principle of a KD tree is it looks something like this. What a KD tree does is it slices one dimension at a time and kind of splits them. Okay? So we can use the same basic structure of a KD tree to build an optimized high dimensional histogram. So what do? We start off with our entire domain and we pick a dimension and then we split to maximally reduce the bucket variance, right? That variance that I showed you about, that sort of non-homogeneity within a bucket, we pick one of the dimensions and we find a cut that minimizes, that maximizes the benefit, right? Maximally reduces that variance, right? So we go here, let's pick a dimension, let's cut this guy over here. Let's go over here, let's pick a dimension, cut this guy over here. Let's go over here, pick a dimension, cut this guy over here. What this ends up looking like is something that looks like this, right? We end up coming up with a partitioning that takes dimension 1, dimension 2. We're slicing and creating buckets that sort of maximally reduce dimensions. But this is sort of hard to sort of parse, but the intuition is what I showed you before. What we're doing is we're starting off with all of our data. we're iteratively partitioning that data to make it more and more homogeneous between what we're interested in aggregating. Okay. So then what we can do is, for each one of these final partitions, we calculate some aggregate statistic of interest. Whether we're summarizing things with counts, like frequencies, whether we're summarizing things with averages, whether we're interested in doing things like medians, right? The basic principle holds. The idea is taking a high-dimensional space, breaking it up into disjoint partitions, and summarizing those disjoint partitions with an aggregate statistic. Okay? And the way that we do this in this case is using this KD tree iteration. We start at the top, we repeatedly pick a dimension, cut along that dimension. We repeatedly pick another dimension, cut along that dimension. And we go until we sort of hit the number, our storage budget, the number of desired disjoint partitions. So, some of these details, like what statistics to compute, how do I summarize these partitions, in practice, if you're building a software artifact that implements this, you just calculate a bunch of common statistics. The way that we did this is we took this basic theory, which we proved stuff for counts and we proved stuff for sums. We took this basic theory and said, like, can we build this into a software package? Well, what we ended up doing is just calculate all the statistics you care about. All the statistics a typical user would care about. Sums, counts, mins, and maxes. We also toss in a random sample of size k into that little bucket. What this allows you to do is a general data summarization package that takes a data set. A user tells us what they care about aggregating and what they care about what is going to be used to partition the data. We run our KD tree algorithm, calculate some count and a random sample of size k associated with each one of these pieces. And this gives us a nice reduced size sketch of a large data set. So that's a little bit abstract. How does this look in practice? Like, what does this kind of look like if you sort of want to visualize this with real numbers, right? So it takes a data set. Let's imagine that there are two columns, A and B. Let's imagine that A is what we're partitioning on and B is what we're aggregating on, right? So what this is going to look like is it's going to be a tree of partitions. Like, for example, the first one has all the A values. The second layer has A less than 24, A greater than 24. The third layer has A less than 10, and so on and so forth, different disjoint partitions. Each one of these disjoint partitions is going to have a sum, count, a min, and a max of the B values conditioned on those A values. Then associated with each one of these guys is going to be a random sample of data. So this was what we call a partition tree synopsis. And we've been spending a lot of time understanding how can these partition tree synopses be used, and where they are useful for, what they're useful for, and what are some of the theoretical properties of them. So if you guys are familiar with SQL, it turns out that you can answer a lot of SQL queries directly on the partition tree synopsis. You can answer them approximately directly on the partition tree synopsis. For example, I could write an SQL query for saying, what is the average height for people 20 to 45? The way that I can answer that query with this partition tree synopsis is I traverse, again, do the opposite of the construction process. I traverse top down. I find nodes in the tree that align with this 20 to 40 age group. Nodes in the tree, partitions that are completely disjoint, can be skipped because they have no impact on the answer. Nodes that are fully overlapped, I can sort of just fold them into the answer deterministically because I've summarized that entire node, right? I've summarized that entire partition. This is kind of similar to the problem that we had with ages, right? Now imagine I was interested in the number of people on the blue line between the ages 70 and 80 that were there on the blue line, right? I could directly take that bucket, right? So it's really to be able to answer queries on this, you can sort of traverse top down, find full overlaps and no overlaps, and you can kind of skip them. They don't have an impact on the answer. Where the estimation error comes from is the partial overlaps. And for those partial overlaps, what we've done is we've stored those random samples of size k, and they can be used to estimate the impact of those partial overlaps. Okay, so we've built the synopsis that can actually answer a lot of simple SQL queries. These aggregates conditioned on filters of the partitioning attributes, and we can use that, and we can also furthermore put some guarantees on the accuracies of those answers. At some point, this essentially behaves as what is called a stratified sample in the opinion polling world, right? What we've done is we've partitioned the data, gotten these aggregates, and gotten these random samples. This data structure that we've built behaves a lot like an opinion polling problem. You have a lot of approximations that we have to add together and some weighting based on how big those approximations are. So you can calculate an estimate as well as you can calculate the variance as well. So this gives us not only an answer, it gives us a confidence interval. Now this particular confidence interval is an asymptotic confidence interval, but you can also calculate a finite sample error bound on this process. So we have a synopsis that can take a large database. We can answer simple SQL aggregate queries directly on the synopsis with error guarantees. We have a knob that can tune storage, right? That is the number of leaf nodes that we have in the sample size versus latency, right? That's like that's the amount of data that we're processing, and all trading off error. The bigger our synopsis, the lower the error. Okay. So we did a bunch of evaluation on it, and I'm not going to really bore you guys with the actual experimental details too much, but essentially we've run this on a bunch of different data sets against a bunch of different synopsis construction techniques. We've looked at just uniform sampling, standard histograms, standard stratified sampling, a technique called coarse sets, which is from the machine learning community, as well as two research prototype open source systems, right, called DeepDB and VerdictDB that ostensibly do approximation. What we find is that our synopsis structure, right, the simple idea of basically doing a KD tree-like partitioning to construct a high-dimensional histogram, not only outperforms in terms of storage size, also gives us the lowest error compared to everything that we're using. How did we run this experiment? We were roughly speaking controlling for average latency, right? Histograms are the weird ones, but we put that in there just because this is kind of from the same family of algorithms. But roughly speaking, up to engineering differences, we control for average latency, and we found that our technique gives us the best sort of high-dimensional compression that compared to all other baselines. Okay? So, now, there's a bunch of theory around it. The reason that we sort of went through all of the rigor of using these KD trees, there are many different ways to construct partitions, is the fact that we can actually prove something about the nature of this algorithm. We can prove something that not only can you get guarantees on the query error, you can get an overall guarantee on how optimal the structure that we've constructed is. I'm not going to sort of get into that here. Feel free to ask me offline if you're interested in exactly the mechanics about this. Now, another thing that is super important about this particular structure that we designed is that it can easily work in a streaming setting, right? Ultimately, what we've built is a hierarchy of aggregates and samples. And this really means that we can take this data structure and apply it in a high throughput streaming setting. For example, like the example I always give is that for stock trading, right? People are interested in building models that can predict when to buy and when to sell stock, right? The problem is that if you were to actually look at stock data, you're talking about potentially tens of thousands of stock orders per second. Now, not all of those orders are relevant. You might be interested in just capturing broad trends. Are prices going up? Are prices going down? Are there more market orders? Are there more limit orders? You might want to capture these broad trends really, really quickly. This is a perfect use case for a data structure like this. You can take that fire hose of stock market. You can take that fire hose of stock order data, shove it into this model, right? Keep a reduced memory representation of what is going on. You don't have to store all of that data. And simply update our samples, update our statistics, and then propagate the information through, and you can answer queries with accuracy guarantees. So this means that if you're building a high-frequency trading model, if you're building a little AI bot that can make trading decisions, you not only get some features about how things are moving, you also get error guarantees. How far away from real truth is this guy? You can control latency or accuracy in a model like this. So we've been playing around with this with a tool, like I said, a research prototype called DeepDB that is very much used in these kinds of scenarios. And what we find is that our technique sort of blows it out of the water in terms of transactions per second. We can build a system based on these types of synopses that can take in 20,000 records per second, and we've tested this out on stock data. And if you're 200,000 records per second, and we've tested this out on stock data. If you're interested about 200,000 records per second and why we hit that as our goal of what to be able to process, NASDAQ caps out at about 70,000 transactions per second. So we are well above that threshold of processing data. We find that we can also answer queries sub-millisecond, which is faster than, again, open source research prototypes, as well as all of this is with less than 1% of error. So this is super cool that we can take stock data, take the workload that they care about, the types of queries that they're interested in. We are giving them the 95 percentile error on their queries is 1%. So that means that at worst, they're talking about like a 1% error in these estimates. But we're giving them 200,000 records per second processing capacity. All because we reduce the size of the data. You're not processing every single record, you're just aggregating it up and then letting the algorithms hit approximate queries on this database. Okay. So from a theoretical perspective, there's actually something really interesting about this result, right? That is sort of, it just goes beyond my story about histograms. Really, histograms and samples are sort of good at two different things. Histograms are fundamentally good in low dimensions, as we saw, and samples are kind of bad in low dimensions, right? That if you have a low dimensional data set, samples are going to be extremely sparse and not capturing all the different variations. Now, in high dimensional spaces, samples actually exploit the sparsity a little bit more, right? If you think about what a random sample of data does, it hits exactly those hotspots and it sort of zeroes out parts that don't have any mass, right? So by building this kind of hybrid structure where we're doing this KD tree partitioning of the space and associating random samples, we're sort of getting a hybrid histogram in a sample, which is where the theoretical guarantees come from, because these are two really simple statistical sort of pieces, right? They're easy to analyze. But it also gives us this very deep thing that we're getting robustness in high dimensions as well as good performance in low dimensions in terms of estimation. Good. So if there are no questions about that, I'm gonna move on to the last segment in sort of the interest of time. Are there any quick questions? Yeah.
I had a question about what you just talked about, and I was wondering how this algorithm works when you have some I was just looking at the stocks data, I suppose, when you have very rare or extreme events and whether it's able to capture it.
Good. It won't capture rare extreme events. And that's exactly, you can actually look at this P95 error, like there is a steep drop off. If it went P99 error or if it went P99.9 error, there's going to be a great increase in this. Fundamentally, synopses are not going to be good at capturing rare events. That is something that you almost want to build a separate data structure for, right? One thing that we have explored, I have a student right now exploring this, is in addition to the synopsis, build a rare event index. That means you explicitly do anomaly detection on the side to capture the rare events, because you kind of want to do the opposite of this, right? Optimizing for the average case is different than optimizing for the extreme cases. You want to do both. And integrating them all into one data structure seems a little daunting. I think that it's a very good insight that this is not going to work, and there's a reason why we sort of cap out at like the 95 percentile error. It's like the error drops off very steeply.
Can you provide a little color on that previous slide on what you mean by processed?
Good. Process means that this data is ingested, it is loaded, it is parsed, and it gets into the synopsis data structure. That means that you can do 1 over 200,000 is the amount of time needed to take one order record and fold it completely into the synopsis. That this includes everything. This is not just like a isolated experiment, and our implementation uses Apache Kafka. So it's like get the data out of the message broker, parse that data, convert it into some serialized format, and shove it into and update all of the necessary internal statistics in our data structure.
And did you get the data from just one exchange or multiple exchanges?
No, it's only NASDAQ data. So it's one exchange, and it's like they're through their API. So it connects directly to our Kafka server on U Chicago campus. I couldn't tell you what the latency between their API and the real world is, but this was a good proxy for what at least our collaborators in the financial industry told us that was a good proxy for what they do. But there is potentially a latency between NASDAQ's API and our server that is not accounted for here.
Thank you.
And this code is all open source, all of this. So feel free to email me after, and I'm happy to hook you up with one of my students on if you're interested in playing around with this code or the data or anything that we're working with. Good. So the last project that I really want to talk about is how we sort of took this idea of histograms and we went another way about it, right? Like, in some sense, we're talking about high-dimensional data analysis, but we're not talking about machine learning, which is kind of weird, right? So we starting to think about what sort of insights are there from the machine learning community on this problem of summarizing large data sets. So let's sort of think about this again, go back to the basics. What are we trying to do? Fundamentally, in the last project, we're trying to represent a joint probability distribution. So we have a high-dimensional joint probability distribution that is somewhat sparse, and we want to try to represent this with a small number of bits. Are there others? And now there's a natural question if there are other solutions other than what we just proposed, right? This KD2 partitioning is one such solution. So in some sense, we can really think about this partition tree synopsis, right? This idea of building these sort of partition trees as sort of cutting a data set by rows. We're sort of grouping the data set into groups of rows, and then we're aggregating those groups of rows. Now, if you're sort of reading my train of thought, the natural question is, instead of cutting along rows, could you cut along columns? Could you sort of decompose a data set vertically and summarize each one of those vertical pieces? Because we already talked about that histograms work really well in low dimensions. Is there a way to sort of cut up a data set into sort of low dimensional components that we can apply simple techniques to sort of figure out? Okay? So to do this, we basically rely on one statistical insight, that every joint distribution can be decomposed into a series of one-dimensional conditional distributions using a decomposition called the chain rule. So if you have P of x, y, z, it's P of x times P of y given x times P of z given x, y. Now, if we look at one of these components, if we look at any one of these conditional components, they are simply a function. It is simply a function of everything that it's conditioned on, right? So for example, P of age is the frequency for a specific age. It is a function that given a certain age returns how prevalent that age is. Now, P of country given age is going to be the frequency of a country given a particular age. P of last login given age and country is going to be the same, just kind of do this thing, right? So it's a one-dimensional function. It spits out a scalar value. It spits out a probability given all of those components. So now if we think about this as a machine learning problem, right? Machine learning, neural networks, for example, are really good at approximating pretty much arbitrary functions, right? What if we could represent each one of these conditional components using something like a neural network? Rather than building up these histograms, rather than building these partition trees, rather than spending a lot of time proving things, why don't we just come up with some sort of a model that can represent each one of these conditional components, right? And this chain rule decomposition is exact, right? It's not like it holds only if things are independent. It doesn't hold only if things are uncorrelated. It holds all the time, right? So could we build a neural network to represent this type of a joint distribution? Like, what does that look like? For example, we could generate a training data set of ages and their corresponding frequencies and learn a function, like a p prime of age, that approximates that conditional probability distribution. So if we have something like users, ages, countries, we can just generate a bunch of training data and learn that type of model. So that was actually going to be the starting point of our next project. Could we use machine learning to summarize a data set by using a neural network architecture that approximates each one of these conditional probability distributions? And by decomposing them into the conditional probability distributions, the idea is that each one of these components is going to be denser than the original distribution in the first place. So we have P of x, P of y given x, P of z given xy. Essentially, this neural network is going to capture, approximate them into a P prime of x, P prime of y given x, P prime of z given xy. So now, the one caveat here is actually kind of similar to what we saw with the partition trees. You have to pick a variable ordering up front, right? To use the chain rule, you have to decide in some ordering of these variables. And you have to order these variables in exactly the same kind of a way. You need to pick them as these are the important things to condition on, right? So even though we're using machine learning, a lot of the theory that we built up for that partition tree project matters a lot here because you need to know what variables are good to condition on and what are going to be correlated with the things that you're trying to aggregate over. So essentially, you can think of it as the same mechanism. This is a decomposition of the data set to eliminate sparsity. these chain rule decompositions, these are much denser representations of the data set than the original joint distribution. So once you get these types of approximations, right? Once you get these types of approximations of the original distribution, of these original conditional distribution, you just simply have to take the product of all of them to be able to evaluate a certain frequency. For example, I might have a query where I want to know how many users have age 10, country USA, and logged in yesterday. I simply have to take each one of my components and fill this in. I need to see the probability of age 10 and the probability of country USA given age 10, and so on and so forth. And when I take that product, it gives me an approximation of the probability of that query. So there are a number of problems in this sort of mathematical formulation that we ended up fixing using a lot of engineering hacks. For example, there's a natural problem with the problem of progression, right? With projections, right? So suppose I was interested in only users from the country USA. The problem is, the way that we've sort of posed this problem, there are going to be some issues, right? We'd have to do a lot of different products and sum over them, right? We'd have to calculate age is equal to 0 to 125 and the conditional of age is equal to 0 to 125. We fixed this with a really neat trick that I'm actually kind of proud of because it turned out to be really, really simple and just exploiting the fact that, a neural network doesn't really care what it's approximating, right? So we actually came up with a special value that represented a wild card. We came up with a special value that represented a wild card that was representing the entire marginalized distribution. So age is equal to star, the probability is equal to 1. P of country given age is equal to star is just the frequency of a country. So we represented this as like a special symbol, like the same way we have an age is equal to 10, we had an age is equal to star with special semantics over there. We also had an issue with the range queries, right? You might be not only interested in just marginalizing out age, you might be interested in a range of ages. How do you solve this problem? Turns out you can solve it using something called importance sampling. You just basically use Monte Carlo evaluation to repeatedly sample from these conditional distributions and integrate them together. So this project was very, very different than our previous project, right? We sort of took an empirical approach to it. We sort of knew from the start there was not going to be any deep theory about this. We're not going to be able to prove anything about this. But we wanted to find use cases where something like this would work, right? The idea is that we're taking an entire data set and we're training a neural network to basically approximate this data set. It's kind of a weird concept, right? That it's like usually we train a neural network to do something. In this case, we're training a neural network to approximate the data set itself, right? And this comes with its own like pros and cons, right? That it's like a very costly upfront process. It can't be updated in the same way that we were talking about rapid fire stock ticker symbols. But we were just interested in where would something like this be useful? Suppose we got a really, really good compression, right? Where would something like this be useful? It turns out that there's a sub-problem in database design, the design of database systems called query optimization. Essentially speaking, a database system, when you give it an SQL query, it has to simulate a bunch of different execution methods, if you will, to understand what is the best way to execute this query. Now, it can't just run these queries over in all these different ways because that's kind of defeating the purpose, right? That means you're expending the original runtime to do it. So it sort of has to simulate this in a cost-efficient way. And the way that we usually do this is using something called cost modeling, or what, as you'll find out, is basically a data synopsis. You take your original data set, you sort of summarize it down. Usually this uses something like traditionally solved with histograms. You summarize this data down and you simulate over those summaries different execution paths. Then you pick the best execution path and you run it over your full data. So this is called database query optimization. Almost all databases today have some kind of a query optimizer. Some of them are more sophisticated than others, but essentially they leverage they leverage a data synopsis. And within this problem, basically the core synopsis problem is something called cardinality estimation. How big are things? Generally speaking, if a database has to process more data, things are going to be slower. So it needs to estimate the size of intermediate results. So we used this model, this neural network model that we just proposed. We used it as a drop-in replacement for a database query optimizer. We used it as this cardinality estimation component in this database query optimizer to see, well, what is the impact if we got really good synopses, really fast and highly accurate synopses, what would actually happen? So we ran, again, a bunch of experiments on well-established database benchmarks. We had a bunch of data. These are the statistics of the data. We had a bunch of queries over that data. And we compared, again, to a bunch of different database implementations now to understand how does this core component of a query optimizer work, right? These are some research. This is an open source database system called PostgreSQL that you might see in your classes. This is a database that we're not allowed to name for publication purposes, but it starts with an O and ends with a RACL. So like that's that database system over there. So we compared this database query optimizer with our new synopsis component, right? And this bold guy over here is us. We show, like our histogram project, that we have significantly more accurate results. We have significantly more accurate results than previously published work, as well as open source things. And we did actually a very long study on this guy. We have a ton of different baselines where we compared against systems out there, we compared against approaches, we compared them on many different axes, including storage and latency and accuracy and all of them. And we found that actually a neural network does better than anything that we ever designed, right? Any amount of partition trees and all of that, right? A neural network just across the board was just the best synopsis we could build, which makes a ton of sense. Machine learning models have a natural ability to sort of compress data, right? They're trying to look at the most concise representation of your data set to be able to predict something, right? Because any excess data is going to overfit, right? So if you're controlling for your validation error, you're kind of ultimately compressing your data in a weird way, right? So there's kind of a natural compressive tendency in these neural networks, and we found that this sort of a method was better than anything that we could design. But on the other hand, the downside is a lack of guarantees. You have no guarantees about when it works, no guarantees about why it works. Will it work for this data set versus that data set? Who knows? But it's kind of an interesting, exciting result that there's an opportunity to sort of reinvent the way that data compression and data summarization is done with these new tools in neural networks. So that's kind of, I sort of jumped the gun on the slide a little bit, but essentially, this seems like it invalidated our previous work. It really hasn't, because it can't handle updates. You have to retrain this model anytime new data comes in. It doesn't have any guarantees at all. It requires the data is also readily featureized, right? It only handles numerical data, right? How would you put in string value data, for example, into a neural network? You'd have to figure out some way of representing that numerically. And even more sort of damning, it requires specialized hardware, right? The fact that you need a GPU for something like this almost makes it not useful in these database settings. Now, if you tell somebody who's building a standard database that you need to buy a server with a GPU, that's a huge ask. So there's sort of like realistic reasons why you can't just use this. But in short, the empirical numbers gave us a lot of interesting thoughts that it's like maybe the future of data compression is using machine learning as a core component. So that's pretty much the talk that I had. I started off with this sort of like very simple mathematical insight, like something that came out of one of my classes, right? That like histograms don't really work well in sparse and high dimensional data. And we talked about two different ways that we approached addressing it. Can we sort of build something that looks like a histogram, and then can we build something that doesn't look like a histogram at all, right? And what are the sort of accuracy properties of this, and what does this tell us about data compression? And really, again, we sort of, with all of these details, we lose sight of the big picture. Really what we want to be able to do is to take a large data set and synthesize it into something much, much smaller, summarize it into something much smaller, and do approximate processing. And there are many applications of this, right? There are applications in stock prediction, there are applications in machine learning, there are applications in visualization, as well as there are applications in data-intensive systems themselves. Compilers and databases often have to simulate the effects of different programs, and synopses can help them do that. And really, if I want to give you one take-home message, it's that high-dimensional data is almost always sparse. So any data summarization technique that you have has to be able to exploit the sparsity that is natural and inherent to high-dimensional data. So essentially, this comes down to decomposing the space. The same way that we saw this in low dimensions, like you have to decompose the high-dimensional space. So that's pretty much my talk. I want to credit the two students who pretty much drove this work. Stavros Sintos is my postdoc at the University of Chicago. Shi Liang is also my senior PhD student at the University of Chicago. All of this work happens in the ChiData group, where it's about 17 people. We have 14 graduate students, 3 postdocs, run by 4 faculty. We do a variety of database research, not just on histograms. We do work on edge computing. We do work on data markets, buying and selling data. How do we value data? We do a lot of work on data governance. Feel free to talk to me about any of that. I'm always happy to chat about anything data related. And that's pretty much it. I think that I'm happy to take any questions from the audience.
Thank you, Sanjay.
Thank you.
Okay, Zoom audience. Any questions?
You said the software or the code you wrote is open sourced. How do we get a copy of it?
Oh, definitely. Do send me an email and I will point you to my graduate students, because like it is open source in the academic sense that it's all on GitHub, but you definitely need help getting it installed and run. So just send me an email. I can point you to both projects, both the neural network for density estimation as well as the partition tree project. Both of those projects are open source, as well as the data that was used in both of them.
Thank you.
Have you tried it on any other data besides stock data?
Yes, we have. We have tried it on a lot of geospatial data. So we've done it on a lot of things like taxi data and anything that essentially anything that there's like a natural redundancy that is like, the stock data has a natural redundancy just because like a lot of securities are highly correlated with each other, like one goes up and like all of them go up. The same thing goes with geospatial data as well. So like taxi trips, again, if there's a concert, there are a lot of very, very similar taxi paths, again, highly compressible. Those are the types of data sets that we've run it on. We are really interested in running experiments on on activity recognition data is the next big thing that we're interested in. That means that we have some sort of a webcam, or you have some sort of a security camera that's capturing people interacting in the real world. Like again, like doing a lot of different things, a lot of pose information, like a lot of movement information. How do you sort of compress them, because you want to minimize the amount of data that you're sending over a network, right? So that's another data set that we're really looking at. But we've done it on a handful of different data sources. These are sort of the two most compelling examples I presented. Thank you.
So we have a question from Tanu. So are these techniques applicable to equi-depth histograms?
Yes. Okay, good. I can actually talk a lot in detail about the difference between equi-width and equi-depth histogram. In short, equi-depth histograms do not solve the problem of sparsity. Equi-depth histograms assume, like, we can also work by first principles, right? Histograms exploit smoothness in a distribution. Equi-width histograms assume that within an equal-sized bucket, you have similar frequencies. Equi-depth histogram assume that within an equal-sized quantile, right? That means that's not over the domain, that's an equal-sized quantile, you have smoothness in density, right? So it works great in something like a power law distribution where you can convince yourself that an equi-width histogram would have a lot of high variance, but equi-depth histograms still suffer in the case of sparse distribution. And in fact, actually the plot that I showed you took the best of equi-width and equi-depth. It was not just an equi-width histogram, but it's an awesome question. I'm happy to chat the theory about that and why that's the case. But we did that first entropy diagram that I had that was that scatter plot actually took the best of equi-width and equi-depth.
Follow-up question from Tanu as well. Yeah. What are the characteristics of NYC taxi data?
Yeah,
Do you know how many unique values?
That's a good question. This is a question that it's probably in one of our papers. We have 5 dimensions, 7 million records, 2,000 random queries. The actual number of distinct values and the number of values per dimension, I actually don't have that off the top of my head. That's something I can easily look up right after this. So send me an email so I won't forget that.
Any other questions? Okay, so this meeting is getting recorded, so it'll be posted for everyone to watch. Sanjay is going to hang out here. We have this room until 2:30, so if any of you guys want to hang out and chat, even via Zoom, I'll stop the recording, but I'll leave the Zoom session on. He's here. So thank you all for coming, and we'll see you guys next week.
Yeah, thank you guys all for having me.